started, and since Thursday to Tuesday is a really long time, so it's good to look back and see where we are. So what we did last time was we looked at the solution of the biharmonic equation, which is here, if you want to look at it again. And we tried, I said that we consider in this class two forms of equations. One, using power series or polynomials, and the second one, separation of variables. So we only considered the first part, and we did one example that at the end became a little bit controversial because you have forgotten the earlier material in the semester where we actually looked at the gradient of displacement and we decided what we consider a strain and what is the rigid body deformation. But now we discussed, and I think we are all okay, including Tom. We talked about it last time and it's all clear. So what I want to do today is to do another example, but this time I want you guys to work on it more on your own. And my motivation is that, of course, there is a new homework assignment. It's only 3 problems, so it's not as long as the assignment over the break, which I'm still grading because it's very long. But it's kind of, this is going to help you to very easily go through that. That assignment has 1 question, which is derivation, and then 2 problems, which are similar to the examples that we are looking at. So what we are looking at today then is the solution. Still, we start with the power series solution, but a different problem. And then hopefully we get to introduce the separation of variables. And I plan to solve one small problem with that for you because that can get pretty hard to write down pretty fast. So, okay, so let's start with the example. So with that, so example number 2. So I just start directly with the example. And I write here that this example is the solution of biharmonic equation. We are still just considering Cartesian coordinate system. We haven't talked about the polar coordinates yet. And it's a power series or polynomial. Solution. It means that you start off with assuming that it's polynomial. And the example starts with a form which looks like that. So now, that's all you need to know. For area stress function solution, all you need to know is a field, a scalar field. Now basically, you all have written up this. So we had the steps 1, 2, 3 in the last one. What I want, Prabha, no panic. What I want for you to just go through it together. So it's a pity that Clay is not here and Farshad is also not here. So I don't know, would you be comfortable just working alone, or do you want to join Tony and Mike? And the same goes for Mika and Cody. I don't know if you guys like to work together. Maybe it would be easier, I think, to work together. So try to kind of form groups of 2 or 3. Step number 1.
So basically, she just gives the area stressor.
I'm certain that you have forgotten the steps, so the way to do it is go back and then from time to time I turn on the screen so you can check. Basically, this is how it's going to go. Would that be possible? Derek knows what I'm doing, so we can talk to him also. Use plane stress. So if you are calculating a strain, use plane stress. Okay. Is everyone finished with step number 3? Yes? Not yet? Almost? Okay. So you can check the earlier steps here if you are done with number 3.
Gives you both U with del U del X. So you have U with del over del E del X.
If you are at the end of step 3 and going to 4, please raise. Who is not finished with the step 3? Before going to displacement solution, please don't go to displacement because we want to make some simplifications in notation, so don't go that far. Otherwise, I think it would be hard. Okay, so this is the first 2 steps. I looked, everyone seems to be good there. Here are the boundary conditions. Traction free on the top and bottom, and then you have to have boundary conditions on all boundaries, right? And what type of a physical problem does this represent? Pure bending, right? Perfect. Since we want to compare this to a strength of material solution, let's calculate the resultants before moving forward from the tractions that you obtained on the boundaries. So if you look at both sides, how would you calculate the statically equivalent resultants? I'm sorry? Exactly. So so if you want to get Rx, why does it move? Interesting. Oh, what happened again? So calculate Rx, Ry, and M in this case. So I resolve the issues with I have to start this over because it's doing strange things. Okay. Looks better. So we want to calculate the resultant force R and moment M for the traction distribution we did this last time too. For me it's boundary number 2, it may be different for you. And how much is it? Yeah, this is simple, right? I'm writing the formulation so that for the problems you have in the homework, you have everything written up. How much is ty dy? It's also 0. There is no ty component, right? It's all 0. Let's look at the boundary conditions. Don't forget, if you see that it's 0, you have to write it down still for boundary conditions, right? You cannot just say, because it's 0, you just don't write it. Don't do that. It's like in finite element software, you also have to, even if things are 0, you have to specify it on that boundary. You cannot just leave it out. Correct? Okay. How about M? So let's take the moment around a point to the far right of the beam. So, or the domain. Choose the point. Doesn't matter, right? You can choose any point. If you do that, it's easy to write it down. I'll take this as negative m. So if you do that and substitute for tx, check that I'm not making any mistake. You should get something like that for m. So this coefficient that we had in the area stress function, you see it is related, it shows up in the moment. So similar to what we had before, that for the force, the coefficient would show up there. So if we use this m, let's rewrite sigma xx, sigma xy, and sigma yy using this notation. And check that I'm not making a mistake, right? Those two are 0, that's easy. So basically I'm just replacing A03 by m over 4, negative m over 4 c cubed. That's what I'm doing. And then there was a 6 in front of it. So that's why we have 3. Okay. I'm doing that so later we can easily compare this to the solutions that you are more familiar with. That's my motivation. Otherwise, there was no problem of keeping A03, other than also that it doesn't have an immediate physical meaning. If you just have a A03 floating around in your equations, you don't know exactly what it is. But when you see M, it's kind of obvious what it is. So now we can go to step number 4. We use plane stress. Solution. Now use this formulation. So if you already have it, just try to just use sigma xx in terms of m. So later on we can again compare it to the strengths of material solution. How many have a step 4 already written down? Okay. Let's go back. Yeah, you're right. Let's look at the problem. I'm sure there is a reason I put a negative there. So I should put the m actually here. So I'm taking m to look like this. That's why. With the positive convention in. Thank you actually for mentioning that. And then the m from the traction is the opposite to this m, right? So something that Zach asked me and I had forgotten to talk about is that I have to draw the m here, so you see why the m is negative in the resultant. So I'm using the positive convention that you are familiar with in a strength of materials for m. So that's why then that resultant would be the opposite of m, right? This is just because of the convention. That's. But thanks for mentioning this, Zach. Okay. So. Check to see if everything is what you have. And now the last step was to calculate the displacement, and that's we keep this for a couple of minutes. For displacement, please go through the motion. Last time it looked like, it wasn't as obvious how to put together the solution.
Yeah, so what I'm saying is, before you had, we get certified, right? So now we have, with respect to y, this, here is y. So 4 is constant. Now let's say function of x, we take this with respect to the root of this with respect to y, we get f prime y equals 4, then the function of x. Because that's how we're getting the y, and we still say that it's not going to be right. You actually have to do the math.
Oh, why does it do that? Again. You are checking, right? I'm making mistakes. So does everyone know how we got here? Yeah.
So I know with the condition, the dxy condition, that you have to have some form of fy and do that. I don't know how you do exactly that.
It's similar to what we did last time. So you need to use the fact that fy is a function of y and gx is the function of x. You want to go through the steps? Could do it after the class. Oh, okay. So last time we said, because if the derivatives of two functions, which one is a function of x, the other is the function of y, are equal, they have to be both equal to this derivative should be a constant. Otherwise, this cannot be the case. This is the trick that we used last time, and we took the constant to be omega 0 or negative omega 0. And then if you use that, then you get to something like this. Make sure you know how to get there, because in the homework problems, of course, you need to get there, right? So Should I write this down, or you are okay with that? Oh, yeah, you're okay, right? Because here the difference is that when you take derivative of v with respect to x, or u with respect to y, you get also a function of x. But this is also just a function of x, so you can combine that with gx. So these are all functions of x. On the other side, you have a function of y, and since the derivatives have to be equal, it has to be. If for whatever reason you don't remember how to do it, I can do it after the class. Show you exactly how you would get that. Now we got here. So what do we see here? We have this part again. And what did we say last time this was? So I tried to convince you very hard what this was. Is it just rigid body motion, or what are we missing when we just say it is rigid body motion? I'm sorry, I didn't understand. Infinitesimal, that's the point. So going back to the discussion we had with Tom at the end of the class, you remember when we were separating a strain from rigid body motion, everything was valid because we considered the deformations to be small. So if you don't say that, really this is not correct. So this is infinitesimal, so don't forget, or if you don't like the word infinitesimal, just say very small, just use something that shows that you are aware of that, right? That's particularly a hard word for me to pronounce always. So this part is the infinitesimal rigid body component of displacement. And last time I even showed you that, if you look at the gradient of just this part, I just repeat it again because it's nice to see. You see that it is skew symmetric. So this is really, and then U0 and V0, of course, they are translations, right? So then what did we say? How do we find them? Now we have this solution, but there are things which we don't know how to find them. What did we say we would do to find them? What's the name? Fixity conditions. So we need to apply fixity conditions. I don't know why today's really not working now. And how many fixity conditions do we need? Yep. Now, we have this situation. So if I draw the domain, because my goal is to compare the solution with something that we already know. So if I draw the domain and I just if you want to compare it to a problem that we are familiar with, what kind of boundary conditions should I put? What problem are we familiar with which looks like that? What kind of beam is kind of easy to solve? Simply supported. That would be a good guess. And when we, in the very beginning, in the semester, I asked you to review beam theory. Do you remember? A while back. And then, what do we consider as a beam? When you use strengths of materials, what do you consider a beam? Is it a two-dimensional domain really, or is it a one-dimensional domain most of the time? It's one-dimensional. So if you want to compare this two-dimensional domain to a beam, which is kind of one-dimensional, we need to kind of look at one of the lines, one horizontal line in our domain. What line do you think would make best sense? Yeah, to take the beginning, to take the middle of our domain and try to compare it to the neutral axis of a beam. If you don't know what the neutral axis is, you haven't reviewed the strengths of materials as I had asked you to do in the very beginning of the semester. But that's the middle section of a homogeneous beam, would be a neutral axis. Anyway, so basically to make the story short, let's make this simply supported so we can compare our results to something that we already know from a strengths of materials. So if I put these conditions here, so I say this is L, so I say okay, U has to be 0 as at negative L and 0, and V has to be 0 at both ends, so one is a roller, so only V is constrained. And if we do that, we get U0 equal to 0, V0 would come at negative 3m L squared 4e c cubed, and omega 0 is also 0. So when you study bending in elementary strengths of materials, there is one parameter that you calculate from the geometry of the beam, which do not really appear in our formulation. Do you remember what it is? What is it? The area moment of inertia. So it's useful to calculate that and see how that is related to the parameters that we have in our beam. So if you look at if you take this as a beam, the cross section is like that, and then let's look at just the unit kind of thickness. So the area moment of inertia is so Alex, is that something you have also you've seen?
Not really.
No, and Gerald, no, right? Yeah, so here it is, area moment of inertia. I guess for us, like engineers, we have seen this from so early on that it's even hard, to. What I just thought about you guys with background in physics, it's probably Clay wouldn't know about this either. But I can explain to you what it is. So basically the formula for a rectangular cross-section is 1/12 the height cube times thickness, which is equal to 1 here. And then I hope that now you feel very happy to see a C cube. So all this C cube we are dragging with us, it's because it is related to the area moment of inertia. But Alex and Gerald, so this is related to you. If you take an area element, you calculate the moment of that with respect to this neutral axis. So that gives you this area moment of inertia. So you take an area element and in your cross section, and then multiply that by the distance squared, and this integral gives you area moment of inertia. So now, if we take I equal to, if I is 2/3 C cube, go back and write sigma xx. You have it. We calculate it. You all calculate it by yourself. Then we change A03, we express that in terms of the resultant energy. No. So I want you to look back at your elasticity solution. Sorry, I confused you. So you don't need to remember analysis or essential material. Look back, you have to know it. We all calculate this together, right? We do that. So look back, and now having I try to express that just in using I instead of CP. That's all I'm asking. You feel relieved now, right? This looks similar to what we had before. Now, if you never saw this in a spatial materials, you don't look at also fun. Yeah, that's why I put word one. That was not just to make you inside, right? It was to kind of so that you can use this knowledge in class, because that's so if you do that, you get, let me write the original sigma xx. So it looked something like that. So if you just substitute for I, you should get the very familiar formula that we all know about, right? And of course, 0 is 0, so how about U? So if we substitute for I, we can also write rewrite U and V. Does this look familiar? No. And why not? Does it look familiar? It always looks like that. It didn't look exactly like that, U and V. What is the main difference, if you remember? Especially if you just took candidacy exam. What should I do to get our familiar displacement solutions from beam theory? Yeah, so why do we have this Poisson's ratio? That's a good point. Why do we have this Poisson's ratio? We didn't have this before, did we? Yeah, because in the beginning I said we really look at it one-dimensional. We are not really looking what is happening exactly in the other direction. So we never saw this Poisson's ratio showing up there. So if you take the neutral axis, if you take y equal to 0, everything looks very similar to what you had before. What you should have told me is actually u. We never even look at u in beam theory, right? The displacement in the x direction, we don't care about that. We always consider the displacement in the y direction. So if you set y equal to 0, so if we look at our general, I have no idea what this is giving me such a hard time today. It's just getting old, this surface. So displacement solution for x-axis, which is the neutral axis of the beam, we have to set y equal to 0, and then in that case we get u is 0. I thought you would all point out to that. I mean, how come we have a u? Like in beam theory you never saw that. So I just hope that you appreciate the a different level of understanding of what's going on. So going from a very general solution to something that you already know, and then discover that you can actually recover what you knew before. Now knowing much more about how you got there and what is involved. But at the same time, I also like you to see that even a simple problem like that, how long it takes to actually go through it. So this looks identical to what you have seen before. So before finishing this examples up, so the next is basically looking at homework. For you, the next example is homework on your own, or if you work on a group. So what happens, I just want to address this. Suppose that you would want to solve a problem which is like that. So to develop a solution for the problem below using area stress function approach. And the problem would look like something like that. So you want to develop a solution here. I mean, in the first glance, nothing is wrong, right? You have a domain. You have three of the boundaries are what? In terms of boundary conditions. Traction free. And to the left, displacement is 0. It looks very straightforward. Now the problem is, if you want to translate this to a beam problem, like what we just did, is it enough to just say that the displacement at the end on the left side of the beam is 0? So there is, you need to apply a magic here. So again, if you are looking at it at this as a 2D domain, everything is fine. You just say, okay, at every single point on the left side, the displacement is 0. You fix it. We talked about this before. But if you want to compare this to beam theory, if the length is much larger and you want to get the solution for neutral axis, you cannot really do that. Because if you say that at that one point, just the displacements are 0, what will happen? It's like a hinge, no? It's not going to work, because in the 2D domain, all those points, which are infinite number of them, they're all going to have 0 displacement. So everything is okay. But in the neutral axis, when you compare it, that will not be the same. So what do we do then? Yeah, so you have to make the slope equal to 0, because that kind of accounts for the other points which are above and below that one point here, because you are reducing the whole boundary condition to one point. And this one point, if you just say u and v are equal to 0, you are not doing justice to that boundary. It's not the same. So just to have that in mind if you see any problem like that. So I just write maybe here, you know what I wanted to say, and I think it's clear for us conceptually. You need to do that. If you are taking 2D domain, not a problem. You're doing as usual. No, moment? Yeah, exactly. No, we don't care about, I mean, moment won't be a boundary condition, right? But we need to have a boundary condition. So like what we did before, I just put a fixed boundary there and everything was fine. But here it won't be the same. Because I think conceptually it should be clear for you. Fine. So I forgot I think maybe in your homework you have one problem like that. So now the question is, should we start the other solution or not? Okay, maybe we stop here because we only have 5 minutes. I don't know how far we can go. If you have question about that part of the solution which I didn't detail, it's now a good time to ask me.